In this section, we're going to talk about how to define lines and planes in space. Now, in the plane, it's convenient to talk about a line based off of its slope. If you know a point on a line and its slope, you can uniquely determine that line. However, in space, it's more often convenient to refer to things not with a slope, but with a vector in the direction that you wish to go. So, for example, let's say you wanted a line that passes through the point P. And let's just say that P is given by x1, comma, y1, comma, z1. Okay. All right, well, the line through that point is the collection of all points that are in the direction, well, that are in some particular direction. Okay, so what direction do we want? Well, if this was in the plane, we would say, oh, we want all of them along the direction of this slope. But in space, what we're going to say is we want a line through that point in the direction of the vector v. Okay, so what's the vector v? Normally I would say this is v1, v2, and v3, but to keep things consistent with the usual notation, we're going to give this the vector notation instead of v1, v2, v3. We'll call it a, b, and c. And we'll see how that looks here in a moment. All right, so you have some space. You have a vector, which is giving you some kind of direction. And let's say you want a line that passes through this point P, which is in the direction of that vector. What that means is you want all the points that are from this point here going in that direction. Remember, this vector that I've drawn here is not a unique vector. There's infinitely many vectors that are still the same as this vector depending on where you start them from. So here, instead of starting it from here, let's say I started it from here. Well, these are still considered the same vector. So by saying we want everything to go in that direction, we're saying we want everything to go in that direction. Okay, so what we want is our line is all the points that are in the direction of that vector. Now remember, when we say they're in the direction of that vector, that means that the vector from the point P, which I'll denote here as P, to this other point is just some scalar multiple of this vector. Let's say, for example, this vector was 10 units long. Well, this might be just 1 unit long, 2 units, and 5 units, and 7 units, and 10 units, and so forth and so on. You could also go backwards. After all, when you scale a vector, which is what we're doing here, scaling it, you can also scale it with a negative, so you could also go backwards. Oh, well, sure enough, that does seem to define a line. From this point, all the points in that direction, and of course that does mean in the opposite direction if you scale by a negative as well, that does define a line in the way we typically mean a line, going forward and backwards in both directions. It's forever. Okay? So if that's what we want, how do we denote that? We want all points. Here, that one's called P. We'll call some random point on the line, we'll call it Q. We want all points Q such that any vector, and you know what, let me give Q a label. Q is equal to, I'll just call this one, this one is x1, y1, z1 because that one's a specific one, but Q is any point on this line, so that's just the typical x, y, z. Okay, so here we want all points Q, which we can denote as x, y, z, without the subscripts, such that any vector PQ, starting from P going to Q, is parallel, in other words, going in the same direction as the vector V. Okay. Well, remember, what does it mean for two vectors to be parallel? Well, it means that one is a scalar multiple of the other. Like we said, it could be an eighth of the initial vector, or a half, or 10 times the initial vector, or even scaled by a negative. You could say it's times -3, -3 times that initial vector here. Okay, so that means that we want the vector PQ how did I manage to misspell the word meaning? Meaning that PQ is equal to some scalar multiple of the vector V. Here we can call the scalar anything we like, but we're going to use the letter T, and we're going to see why that's the choice we use in a moment. Usually for a constant you would use C, but C is already being used. Why do we like T? We'll see that here in just a moment as well. Here, since V is equal to ABC, that's T times ABC. And since that's just a scaling of a vector, we can just distribute that scaling factor to give us the vector TA, TB, and TC. Okay. Oh, but that's just a vector from P to Q. Don't we usually write a vector from something to something else as just being the vector from in standard form, meaning we take the first component of the terminal point and subtract away the first coordinate of the initial point. Right? That's what we see in a previous section as writing a vector in component form. Okay, but the vector PQ is simply given as, again, we're taking the terminal components and we're subtracting away the initial components. From P to Q means you start from Q and subtract away whatever P was. Oh, okay. So this is one way of expressing PQ because it's literally how you write a vector from P to Q. But this is how you write PQ giving me the conditions that I want. I want PQ to be parallel to this vector V. That fits the description in the direction of that vector. Okay, so if both of these describe Q, both of these describe the vector PQ, shouldn't these two be equal to each other? Okay, so let's do that. So that means that the vector x minus x1, comma y minus y1, comma z minus z1 is equal to the vector TA, comma tb, comma tc. But for two vectors to be equal, that means their components are equal. Thus, we have x minus x1 equals TA, y minus y1 equals TB, and z minus z1 equals TC. Here we can go ahead and solve for x, y, and z because after all, the x, y, and z are the things we don't know. Right? We know P, that's the initial point. We're going to know what that is. And V, the direction vector, we're going to know what that is. Which means we know the A, the B, and the C. What we don't know are the X, Y, and Z coordinates of the points on that line. Okay, so we can solve for those. So this, we can go ahead and add that over to the other side, and this gives us X equals X1 plus TA. This gives us Y equals Y1, that should be a Y, Y1 plus TB. And this one gives us Z equals Z1 plus TC. And now this is a parameterization. Thinking back to trigonometry, thinking back to pre-cal, or even thinking back to Cal 2, we see parameterizations as having a way of expressing the individual components of an equation, an x and a y, with respect to some new variable, a parameter. That's why we use the letter T here instead of some other symbol, because T is the traditional variable that's used when parameterizing, T standing for time. So here, these are parametric equations, which leads us to the first theorem for this section. Theorem let L be a line through the point P, which we're going to give as, same as denoted above, x1, comma y1, comma z1 in the direction, meaning parallel to the vector v, in the direction of vector v, which again we'll denote as A, B, C. Then L can be parameterized. L can be represented by the parametric equations that we state above here. This is another one of those instances where usually I'll state the theorem first, then prove it. But every once in a while, if the proof is constructive enough, sorry, you may not be familiar with that phrase. A constructive theorem is one that constructs an argument and a result directly from a definition, doesn't use any other theorems or any other background other than, hey, here's the definition of what we're talking about. Let's construct something that's true. Constructive theorems are often very informative and kind of provide a good lesson on their own. So here, this is every once in a while you'll see me do that, where I kind of provide the proof first to motivate what we're talking about for the rest of the section or even the rest of the chapter. And then we'll state the theorem, which happens to be the theorem that this is the proof of. So here L can be represented by the parametric equations given by x equals x1 plus a t, t-a-a-t, same thing. Y equals y1 plus bt, I guess I'll be consistent, and z equals z1 plus ct, just like that. Sometimes the vector v will be given to you explicitly. Other times it'll be up to you to find it, but finding a vector is usually very, very simple because, well, you're being asked to find a vector between individual points, which we know how to do. So as an example of this, let's go ahead and give this a try here. Let's find the parametric equations for the line that passes through the point to 5, -3. I guess I'll call this one P, point P. In the direction of the vector v, which will give as 1, 5, let me use a different number than that, 1, 6, let's make that a negative, -164. All right, so let's go ahead and do this one together. Here, there's not really much to do. We already know everything we need. Here, P is giving you your x1, your y1, and your z1, the initial conditions of these parametric equations. Here, T is the parameter that you're keeping, so you're not going to substitute anything for T right now. It just remains T. And A, B, and C are the components of your vector. So here, your parametric equations. You just kind of got to remember what this looks like, and that's it. You're done. X equals 2 plus that number times T. Plus -1, we may as well just say -1t. Y is going to equal to 5 plus 6t. And Z is going to equal to -3 plus 4t. And there you go. That's a parameterization, which gives us this line, which travels through that point and has this direction vector. One thing to remember about parameterizations is that there are sometimes where you either do not need or sometimes actively are trying to get away from a parameterization, in which case you would rewrite an equation with respect to just the initial variables. So how do you write the equation without a parameter, how to write these without a parameter, just with respect to x, y, and z, that's actually fairly straightforward. Here, different colors, since that's technically a different part, it's not really part of the theorem. Here, this is, you can just solve for t here. You would subtract your x1 divided by a. So x minus x1 over a, that's equal to t. And over here, this one would be same thing. Subtract your y1 divided by b. Y minus y1 over b, that's equal to t. And then this one here, same thing. Subtract your z1 divided by c. So z minus z1 over c, that's equal to t. And since all of these are equal to t, by the transitive property, that means they're all equal to each other. So putting all this together, x minus x1 over a equals y minus y1 over b equals z minus z1 over c. These are called the symmetric equations. These also give the same information as this, but this gives it in parametric form. This gives it as an equation of just x, y, and z. And again, these are called the symmetric equations. So over here, the question is find the parametric equations. All right? We wouldn't want these. However, in some cases, you want the symmetric equations. The reason we often care about the parametric equations is because as a parameterization, these are all functions of t. And, well, calculus works very nicely when you have functions. When you don't have functions, sometimes things are a little harder to come by. Symmetric equations, however, are often useful because, well, with one less variable and with one fewer equation, it's just, two equations here and here, these are sometimes easier to manage algebraically. All right? So here, the question would be find the parametric equations. This would be the correct answer. However, if we said find the symmetric equations, well, either way, you know your x1 and your a, so those would fit in here. So here, this is the correct answer. These are the parametric equations. However, if the question was to find the symmetric equations, well, it would look like this. X minus, again, your x1 over your a, which is negative 1, equals y minus your y1 over your b equals to z minus z1. Okay, well, minus and minus, we can just say that's plus 3 over c, which is 4. This would be the incorrect answer for the parametric equations because these are not parameterized. This is the symmetric equations. All right. So go ahead and give this a try. Go ahead and find the, and again, I'll ask for the parametric equations. Find the parametric equations of the line through the points P, which I'll give as 2, 2, 1, 0, and we'll say Q is 8, 3, 2. San Antonio and Houston area codes, right? That should be good. All right. Notice I didn't give a vector here, but so what? You have 2 points. All right, so you can always make your own vector. Give that a try. Go ahead and create the parametric equations that are necessary to describe the line given, stated here. Go ahead and pause the video, and when you're done, go ahead and unpause and we'll go through it together. All right, so let's take a look. We have a starting point P, and we're going to go through Q as well. Okay, but we don't know what vector we're using. Okay, but we can find that. Here the vector v is really just the vector from P to Q, right? So we're going to take our destination minus our initial point. So in this case, 8 minus 2. No, here, let me write these first. 8, 3, 2. And then we're subtracting away the components of the initial point, 2, 1, 0. And so that means that we have the direction vector is 6, 2, 2. So there's our v. And so now our parametric equations are nice and simple. X is equal to, take your x1, so there's where you're starting from, there's your point P, 2. Now let's see here, that would be plus 6t. We get y is equal to 1 plus 2t, and z is equal to 0 plus 2t. If you don't want to write the 0, that's fine. You can say 2t. But just to be consistent, I'll write 0 plus 2t. If you just left that 0 off, that would be fine. So there is our parameterization. These are the parametric equations that describe our line. Note that here I went ahead and kept the convention that P is the starting point. If instead you use Q, that is still the same. Right? Here, if you said instead of 2, 1, and 0, here 2, 1, and 0, if you instead you had used 8 plus 6t, 3 plus 2t, and 2 plus 2t, that would also be correct. Because after all, there's nothing that says P has to be the starting point, because there is really no starting point. There's just all the lines on that, all the points on that line. So if we used Q instead of P here, if this was 8, 3, and 2, that would also be a correct answer. If instead you were looking for the symmetric equations, then you would have x minus, and again, it doesn't matter which one we'll use. I'll use the convention that P is the point that we're starting from, but if you use Q, that is also correct. X minus 2 over A equals y minus 1 over B equals z minus 0. And I'll write minus 0 just to keep things consistent, but if you just wrote z, that would also be correct. Over 2 as well, over your c. Note that here, these components of this vector v are our denominators. If any of these are 0, then the symmetric equations are undefined because, well, dividing by 0 makes one undefined. And if they're all equal to that one, well, then they're all undefined. Right? So here, I guess I should write that. Note, symmetric equations are only defined if all components of v are non-zero. Symmetric equations are, let's say it this way, are not defined or are undefined if any component, all it takes is one, if more than one, well, whatever, if any component of v is 0. All right, there we go. Okay. The next thing we want to talk about is, what if we need a plane? We talk about how to find a line in space. Here's some space, and take a line by taking a point and a vector to give us a direction. What about a plane? Well, obviously I can't take a single vector to define the direction of a plane. Planes don't have a direction in that way, do they? Right? A line has a direction, like a slope, but how can you give a direction to a plane? Well, it's true, except it's not. Here's a plane. Here, let's use one of these. I'm going to draw on it, so I want something where it shows up nicely. Here we go. So here's my plane. Let's pretend that's completely flat. Close enough. All right, now this plane contains a bunch of vectors, right? Of course it does. Look, I can keep this vector here, this vector here, and this one over here, and this one over here. There's a bunch of vectors everywhere. Okay, what do they all have in common? Well, they're all on this plane. Well, okay, sure. What else do they have in common? Well, I don't know. What do they have in common? You're the professor, you tell us. One thing that they all have in common, what happens when you take the cross product of any two vectors? You're going to get another vector. Okay, so what? What is the relationship between that vector and these two vectors? Or in fact, any of the vectors that are on this plane. What is the relationship between, if I take the cross product of these two, or really any of these two, you're going to get another vector. What is the relationship between that cross product and any of these vectors? Think about it for a moment. If you have to pause the video, what's the relationship? Okay, the relationship is if you take the cross product of any two vectors, the resulting vector is orthogonal. It's perpendicular to these two vectors. Oh, but if I take that and take their cross product, then I get something that's perpendicular. Oh, but that also works if I take this one and this one. And it also works if I take this one and this one. And if I take this one and this one, and really any of them. Any vector on this plane, if you take another vector on this plane and find their cross product, the result is always the same vector. It's the one that is perpendicular to this one. In other words, it's the vector that sticks straight out of the page. This vector right here that I'm representing with my pen is at a 90-degree angle. It's perpendicular. It's orthogonal to every vector on this plane. So this plane is made up of an infinite number of vectors, but they can all be summed up with this one vector, the one that's orthogonal. This is called a normal vector. If you take the vector that is perpendicular to every vector on the plane, it's called a normal vector. Definition. Oops, let's go back to blue. Definition. Let P, you might wonder, what is that symbol? That's the letter P, but it's kind of curly and stylized. You might say, okay, do we have to write it that way? No, you don't. In fact, it's not even something you'll see in many books. However, for teaching over the last many years, I've noted that if I use the letter P for point and the letter P for plane, people get confused. So I'll use the letter regular P, and that's a point. When I make it all curly, that draws your attention to it. That's supposed to be a plane. If you just want to use the letter P all the time, that's fine, but just be careful because it does get confusing. Here, with a vector, I don't stylize that one because that already has a little symbol that tells you, hey, this is a vector. But here, to tell the difference between a point and a plane, I make it a little stylized, kind of curly P. All right, so let's let P be a plane. That contains the vectors, and we'll call these V1 and V2. Then V1 cross V2 is the normal vector. Sorry, that's bad grammar. I should say is the vector normal. Is the vector normal to the plane. Oh, well, actually, I should say is a vector normal to the plane, because there is a second one. Remember, if you take the cross product in the other way, if you say V2 cross V1, that is also normal to the plane P. It's just simply going in the opposite direction. If you take my illustration here, if you take V1 cross V2, that would stick out this way. v2 cross v1 would stick out in the opposite direction. So you actually have two normal vectors. So is a vector normal to the plane? The other one being v2 cross v1. When you see the word normal, you can also think of that as being perpendicular. And what that means is, it is, when we say something is normal or perpendicular to the plane, that means it's perpendicular to all the vectors on that plane. So that's not really part of the definition, but just sort of as a note. A vector is normal to a plane when it is orthogonal to every vector on that plane. But that's great, because even though we don't have a line anymore, we have a plane, which is made up of a bunch of lines, a bunch of vectors. That's okay. We can still talk about it using just a single vector, which means the plane can still be represented with something similar to this. Okay, so how do we represent that? Well, it's going to reflect a lot. It's going to reflect a lot of the concepts that we have over here. All right, so what do we want? We want a plane. When do we want it? Now. All right, we want a plane. Okay, well, what plane do we want? Well, we want the plane that contains a particular point. All right, there's got to be some point in space that we can track down. Otherwise, I want the plane that goes through this point. All right, awesome. If we don't have at least one point, well, that plane could be anywhere, in any direction. So we need at least one point. We want a plane with, let's say, which contains a point, which we'll call P equals, same as before. We'll call it x1, y1, z1. All right, just to keep it simple. All right, so what is a plane? Well, really, the plane is all the points on that plane, right? So really, we're looking for a bunch of points. We want a plane that contains a point P. Any point on that plane we denote, let's say Q, which is just, well, again, that's a specific point. Q is just any other point that happens to be on the plane. So we'll call that just x, y, z, just some ordered triple in space. Okay, so what we're looking for is, here's your x, y, z coordinate axis. Here's your plane. Of course, your plane does go on forever, but, well, you wouldn't be able to see it if I drew it going on forever, nor would, actually, I wouldn't be able to draw it going on forever. But anyway, so there's your plane. And we know for a fact that we want the point P to be on there. Now, Q is just some other point on here. And in fact, we don't want to be specific. We want Q to represent any and every point. That way, we know we get all of them. So here, just for the sake of reference, I'll draw Q. I'll pick one point and call it Q, but really Q can be any point on here. Okay, so what do we want? Well, we know that this, if we connect the two, that'll form a vector. We know that any vector that we form on here has to be orthogonal to the normal vector. Okay, so we want the vector that starts from P and goes to Q, whatever Q is. We don't know, nor is it going to matter. We want that to be orthogonal, by definition, right? It's perpendicular. It's orthogonal to the normal vector. You say, well, what's the normal vector? Okay, so let's define the normal vector here. We'll use the letter N for normal. And here we're going to use the same as we did in this example over here, where we said, okay, the vector that's giving us directions, we'll call that ABC. Right here. So the vector, we'll call it n for normal, is given by ABC. Okay, well, in our illustration, here's the normal vector, the one that sticks straight out, the one that's perpendicular. That should be 90 degrees. Oh, but what does it mean to be orthogonal? Well, geometrically, it means it's perpendicular. But algebraically, it just means the dot product is 0. So we want to take the dot product of these two and have it be 0. We want n dot pq to equal to 0. Oh, but n is A, B, C, and PQ is, well, you're going to take your Q, subtract away your P. That's going to be your vector PQ. It's going to be x minus x1, comma y minus y1, comma z minus z1. This minus that, this minus that, this minus that. And that's got to equal to 0. Oh, but we know how to take a dot product. And so A, remember when you take a dot product, multiply the corresponding components, first one with first one, second with second, third with third, and then add them all together. So we'd have A times x minus x1 plus B times y minus y1 plus C times z minus z1 equals to 0. Oh, but there we go. That's an equation. And as long as I have all the x's, the y's, and z's, I am saying that as if that's 3 different things, right? As long as I have all points Q, whose components x, y, and z satisfy that all of this is equal to 0, then that gives me all the points on that plane with this as a normal vector and with this as being a known point on that plane. So just like before, I gave the proof first. Now let's go ahead and state the theorem. All right, so theorem. Let P be a plane that contains the point P equals x1, comma y1, comma z1. Curly one, that's the plane. Regular P, that's a point. Let P be a plane that contains the point x1, comma y1, comma z1, and that has normal vector n, which is given by A, B, and C. Then that means that the plane can be represented by the equation A times x minus x1 plus B times y minus y1 plus C times z minus z1 equals to 0. This is called the standard form of a line. If you want to, you can always go ahead and multiply this, multiply this, multiply this, multiply this, multiply this, multiply this. That'll give you ax plus by plus cz plus, and these will just be constants. So you can always just take your constants and move them to the other side. So there are other ways of representing this equation, but when you have it exactly like this, this is often called the standard form of a line. Standard form of a plane. So here we go. Example. Let's say we want to find the equation of the plane that passes that contains the points. And here we're going to give 3 points. P is going to equal to 3, -1, 2. Q, which is going to be given by 2, 1, 5. And we'll say R, which is given by 1, -2, and -2. Just like that. Okay, so here you have 3 points. Just like in the plane, if you have 2 points, you can determine a line on the plane. In space, once you have 3 points, you can determine a plane. Right, same idea here. 3 points is the minimum number of points needed to represent a plane uniquely. Or sorry, to determine a plane uniquely. All right, so let's go ahead and give that a try. First of all, we're going to need to turn these into vectors. All right, because if we're going to go ahead and define a plane using we're going to define a plane. Here's my plane again. Let's flip it over. Here we go. I have these 3 points on it. Those 3. All right, so first of all, I'm going to need to find vectors. For example, that one there and that one there. So if I call this one P, Q, and R, I need the vector from P to Q and the vector from P to R. And that's not, you could have labeled them any way you liked, but I just chose that way, P, Q, R. Okay, once I have those 2 vectors, I need to find the vector that's orthogonal to these, the normal vector to the plane. Oh, well, we can do that by taking the cross product. All right, so then once you take the cross product, that'll be the normal vector. Okay, so if we take PQ, cross it with PR, that's going to give us the normal vector. Oops. That's going to give us the normal vector. Oh, but once we have the normal vector, we have a point on the plane. In fact, we have 3 of them. So now we can go ahead and create our equation in standard form. So give that a try. Start by finding vectors. You don't have to define them the way I did here. You could say, P, Q, P, R. You could say Q, R, P, or whatever. But I'm going to go ahead and do it this way. So you might try it that way. Once you have those, you're going to be able to find the normal vector. And once you have a normal vector and at least 1 point, you'll be able to find your plane. So go ahead and pause the video, give that a try. And once you're done, go ahead and unpause and we can go through that together. All right, so here we go. We're going to go ahead and find the vectors from P to Q and from P to R. All right, so that's the easy part. We're just subtracting. Take your terminal point minus your initial point. So that'll be 2 minus 3. That'll be 1 minus -1. And that'll be 5 minus 2. So the vector PQ is going to be given by -1, +2, +3. -1, 2, and 3. Then we're going to go and find the vector PR. Now again, all of this would have to be true for any vectors in the plane. So if instead of doing that I said P to Q and then Q to R, that would be fine. If I said Q to R and R to P, that would be fine. Any 2 vectors are okay, but since I already drew that, I'm going to go with that. So PR, I'm going to take my R minus my P, so 1 minus 3, -2 minus -1, and -2 minus 2, which would give us -2, -1, -4. Just like that. So now I have 2 vectors on this flat plane. Okay, so the next thing I want to do is I want to find the vector that's normal to this flat plane by finding the cross product of the 2 vectors that are on the plane. Now, of course, I can define any 2 vectors on the plane. I've just chosen these. Incidentally, because this is true for all vectors on this plane, if you had chosen any other vectors, you'll still get the exact same cross product that I'm about to get. So even if you said, okay, I don't want PQ and PR, I want to do QR and RP, that's fine. You'll still get the same cross product I do. So here we go. We're going to take PQ, cross that with PR, and that'll define my normal vector. All right, so let's go ahead and do that. Let's see. I want to do this by using this determinant method, IJK. And then let's see, where's my PQ? Negative 1, 2, 3. Negative 1, 2, 3. Negative 1, 2, 3. And then my PR is negative 2, negative 1, negative 4. And here we go. This will be negative 8i. This will be negative 6j. And this will be positive 1k. And then going back the other way, this will be negative 3i. That'll be positive 4j. And this will be negative 4k. And then once you have those, you're going to subtract them. Take that first vector minus that second vector. So negative 8i minus a minus 3i, that'll give me minus 5i. All right, minus and minus makes that a plus. Negative 6j minus 4j, that'll give me negative 10j. And then here 1 minus a minus 4, 1 plus 4, that'll give me 5k. Now, some people like to factor out any common factors. You don't have to do this. However, so here, my normal vector is negative 5, negative 10, and positive 5. However, notice that that is parallel to negative 1, negative 2, positive 1. All right. Times 5, like that. So 5 times this. So because this is simply a scalar multiple of this one, these two are in the same direction. And remember, we don't actually care about what the vector is in terms of its magnitude. We don't care if it's scaled up or down. We just want the direction. Right? We just want to know, okay, here's your vector. What's the vector that's normal to that? We don't care if we take one that's a little bit longer or a little bit shorter. We just care about the direction. Okay, so here, the normal vector, you can write negative 5, negative 10, positive 5. However, if there are any common factors, you can always factor those out and ignore them. All right? So here you can say, okay, that's equal to, I know that's 5 times negative 1, negative 2, positive 5, positive 1. Or some people even like to factor out the negative 5. That way I can turn these into a positive. So you can say negative 5 times 1, 2, negative 1. So the normal vector could be that one, or this one, you can ignore the scalar, or this one, you can ignore the scalar. And it won't make any difference. In the end, you will have the same equation. All right. So here, I'm going to go with this one because I think this one just looks the nicest. If you use this one, that is the correct answer. If you use this one, that is also the correct answer. But I'm going to use this one because, well, it just looks easiest to use. All right, so now we're pretty much done. We have our A, our B, and our C. Here we have our X, Y, and Z are just variables, so we're going to leave those. And X1, Y1, and Z1 are simply going to be the components of one of our points. I'm going to use the point P, but if you use this one or this one, that is also correct. It won't make a difference. So here, my equation is going to be A, that's going to be 1 times X minus, and I'm going to use this point right here, so that is going to be 1 times X minus 3, 1 times X minus 3, plus, take my B, so that's a 2 times Y minus a negative 1. Let's say Y plus 1. And then minus 1 times Z minus 2. So here I went ahead and used this vector. I could have used this one. If I had said minus 1, minus 2, plus 1, that would also be correct. If I said minus 5, minus 10, plus 5, that would also be correct. As long as they're a scalar multiple of each other, we preserve the right direction, and so we still get the same normal vector. So here we get 1. So that's a times x minus x1 plus b times y minus y1 plus c times z minus z1. And if you use this or this, that would be fine as well. And that all has to equal to 0. And there we go. There's a equation of a plane that contains all 3 of those points. The next thing we want to look at still continues to use this concept of a normal vector. This normal vector can be used to define a few other things which otherwise might sound a little strange. All right. Here are 2 planes. Okay, great. So what? All right, let's say I have them intersecting like that. They cross each other in some way. Okay, so what? What's the angle at which they intersect? Well, I don't know. How do you even define that? How do you define the angle between them? You kind of have an idea what I'm talking about, but how do you define that? Well, we don't really know how to define the angle between 2 planes. That doesn't seem to be, how would you do that? We know angles between lines, but how do you define an angle between 2 planes? I mean, those are different. A line and a plane are completely unrelated. Oh, except that, well, since we're using a normal vector, to define a plane, well then I may not know how to define the angle between the 2 planes, but I can quite easily define the angle between the 2 normal vectors. Oh, so that's what we're going to do. We're going to define the angle between 2 planes as the angle between their normal vectors. So, as an example, here this isn't a theorem or even a definition. That's just, we're going to use that finding of a normal vector to continue to answer a different question. So, example. So, consider the following planes. Consider the planes, I'll call P1, that'll be negative 2x plus y plus z is equal to 2. And I'll say P2 is given by, I guess I shouldn't put equals there because that equals, right? So I'll say P1 and I'll say P2. P2 is 6x minus 3y plus 2z equals 4. All right, so consider those 2 planes. We're going to ask 2 questions about them. The first one a little simpler. The second one seemingly harder, but it actually turns out to be a nice problem. The first one is the obvious one, the one I've been suggesting. We're going to find the angle between the 2 planes. So part 1, find the angle between P1 and P2. All right. So first of all, we need to find the normal vectors. But remember, the normal vectors are simply given by these coefficients. So here that's going to be the normal vector 1, 2, negative 1, because here these coefficients are 1, 2, and negative 1. Oh, so there we go. The normal vector for P1 is going to be negative 2, 1, 1. Now, simple enough. I'll say N1, the normal vector for number 1. That's negative 2, 1, 1. Okay. What about the normal vector for P2? Well, that's 6 minus 3, 2. So those are the 2 normal vectors. So now to find the angle between those 2 planes, we simply need the angle between the 2 vectors. Oh, but we know how to find the angle between 2 vectors. We know that the cosine, so let's see here, recall. We know that the cosine of the angle theta between two vectors is equal to the dot product of those two vectors divided by the product of the magnitude of the two vectors like that. Oh, I suppose this is absolute value there, right? We want that to be a positive. So here that's going to be cosine of theta equals absolute value of the dot product of those two divided by the product of the magnitudes of those two. So here we go. Let's compute what each of these things are. Here, if n1 is equal to that vector, then the magnitude of n1 is given by the square root of, we're going to take each of these, square it, and add them together. Negative 2 squared plus 1 squared plus 1 squared. So 4, 5, 6, square root of 6. Here, the magnitude of n2, same thing, square root of, let's see here, take our components, square them, and add them together. So that's 36 plus 4 is 40 plus 9 is 49. Square root of 49, which is just the number 7. Right? Square root of 49 is 7. Here, square root of 6 doesn't simplify. And then we need the dot product. So n1 dot n2. We're going to multiply component-wise and then add those results. So that's 6 times negative 2 plus negative 3 times 1 plus 1 times 2 equals, let's see, negative 12, negative 3, that's negative 15. Negative 15 plus 2 is negative 13. So here that's going to be the absolute value of negative 13 over the magnitude of n1, which is root 6, times the magnitude of n2, which is that. And so that means that theta, the angle that we're looking for, will be the inverse cosine, or the arc cosine if you prefer that language, of 13 over root 16 times 7, like that. Which I believe at that point we simply pull out a calculator. So we'll grab this thing. I'm in degrees right here. Usually we want things in radians unless they state otherwise. Here, I'll just do it in both. Here we take, let's see, 13 divided by, the denominator would be root 6 times 7. And then we take the arc cosine of that, and that gives us about 0.71 radians. Whenever they talk radians, they usually round that off to 4 decimal places. So let's say 7103. That's a convention for some reason. Most of the time that we write radians in any of these textbooks, they almost always round to 4 decimal places. Why? I don't know. It's just the way that's a convention. There's no reason why you have to do that. That's just what a lot of books do. And if we want to do this in degrees, let's see, degrees, oops, there we go, degrees. Let's see, the square root of 6 times 7. We're dividing that into 13. And then we're taking the arc cosine, and that's about 41.7 degrees. Okay. So either way, we have the angle between our two planes, which again is simply given by the angle between their normal vectors. Now I said I had a follow-up question. Okay, so these two planes meet at an angle. Okay, where do they meet? Well, here's a plane, and here's another plane. They're going to cross, well, they're going to cross at a line. You see that line right on the edge between the two vectors, between the two planes? That line is a line of intersection. Okay, well, that kind of makes sense. If you have two lines, they cross at a point. Okay, so if I have two planes, they cross at a line. Okay, so now the question is, what is that line of intersection? That sounds really pretty difficult. How would I even find that out? Okay, well, how do you define a line? Going back to the beginning of the section, if we want to define a line, we need what? We need a direction vector and we need a point. Okay, well, finding a point is, I guess that's simple enough because all I need is, oh, well, it's going to be a point that's on both of those planes. All right, so really I just need some point that they have in common. I need some point that's a common solution to both of those equations. All right, that might be a little annoying, but that's not too bad. We've solved equations simultaneously before. That shouldn't be terrible. But then we're going to need a direction vector, and that sounds really complicated. I mean, how would I even get started? After all, there's infinitely many direction vectors on this plane. And there's infinitely many direction vectors on this plane. And you want me to find one for each of those? How would you even get started? Goes back to the cross product. Remember, here, if you take the vector that's normal to this plane, it is perpendicular to every vector on the plane. If you take the vector that's normal to this plane right here, then that normal vector is perpendicular to every vector on the plane. So what I want is I want a line that's in the direction of a vector that's in both planes. So how do I find something that is perpendicular to both normals? I take the cross product of the normals, of the normal vectors. So by taking the cross product of the two normal vectors here, that'll give me something that's orthogonal to both. Or in other words, it'll give me something that is orthogonal to the first plane, orthogonal to the second plane, and therefore must be a vector that's on both planes. So here we go. Question number 2. We're going to use the same planes. Let's go ahead and find the line of intersection. Of the planes P1 and P2. Okay. Well, we know the normal vector of P1. I'm just going to write it over here so I don't have to keep flipping back and forth. N1 we found to be -2, 1, 1. And N2 we found to be 6, -3, 2. And we didn't have to work very hard to find that anyway, right? It was just the coefficients of the variables. Okay, so now if we take the cross product of these, it'll give us a vector that's normal to both of them. Oh, but this is normal to every vector on P1. This is perpendicular orthogonal to every vector on P2. So something that's normal to both of these will be on both planes, which is what we want. We want the intersection. We want what's on both planes. So let's go and do that. Let's find the cross product of N1 and N2. I, J, K, I, J, K. -2, 1, 1, -2, 1, 1. 6 -3, 2, 6 -3, 2. All right, so here we go. That'll be 2i plus 6j plus 6k minus, going back the other way, that'll be -3i. That'll be -4j. And that'll be +6k. And now by subtracting those, we get our, let's see, 2 minus a -3. That's going to give us 5i. 6 minus a -4. That'll give us 10j. And 6 minus 6, that's going to give us 0k. So that's going to give us a cross product that is 5, 10, 0. but that will now serve as the direction vector of this line that I'm looking for. So our line has direction vector v equals 5, 10, 0. Again, we just care about the direction of this. If you want to give me any scalar multiple of this, that's fine too. Any scalar multiple works as well. Well, unless you're multiplying it by 0, in which case the whole thing's 0 and everything's, all information's gone. So here, if you wanted to do what? Divide everything by 5, 1, 2, 0, that's okay too. So here we could say, yeah, 1, 2, 0 is okay. All right, so we now have a direction vector. All we need now is a point. So now all we need is a point. And so we need a point that's a common solution to both of these planes. Just some point that's on both lines. That way we have a point that's on the intersection line. Here, if it's obvious to you what a common point is, okay, great, go with that. If it's not obvious to you, a simple way to do that is to simply set one of your variables equal to 0, and then solve the system that's left of the remaining 2. So here, let's say you didn't see a solution to this. Sometimes the numbers just work out nicely, and it's a simple result. However, let's say you didn't see that. Okay, take x and set it equal to 0, or y or z, it doesn't matter. Here I'm going to use x because, well, that's got a big number and I want to get rid of the biggest number. That's just me personally. So here I'm going to go ahead and say, okay, let's go ahead and find a common solution. To the two equations, negative 2x plus y plus z equals 2. And 6x minus 3y plus 2z equals to 4. Okay. In this case, we can set one of my variables equal to 0. I'm going to go with x. Set one variable to 0. I'm going to say, okay, setting x equal to 0. We get the following simpler equation. We get y plus z equals 2. And then we get negative 3y plus 2z equals to 2. Okay. Now solve, that is equal to 4. Now if you solve the system of equations, that'll give you a common point. You already know x is equal to 0 because you set it that way. So now solving this small system of two equations gets you a value for y and z. So here, let me go ahead and eliminate my y value here. I'm going to go ahead and triple the top line. Here, I'm just doing the algebra required to solve this system. Here, if I triple this top line, that'll give me 3y plus 3z equals to 6. And if I leave the bottom y as minus 3y plus 2z equals to 4, I add those two lines together, and that'll give me 0. That's gone. That's going to be 5z equals to 10. Oh, so that means z must equal to 2. That's nice. Okay, so we know our x already. We know our z already. So now we can just find our y. Over here, we know that y plus z equals to 2. Or you could use this one, but that one's got smaller numbers. So since y plus z equals to 2, but z equals to 2 on its own, well, that means y must equal to 0. Right? Because 2 plus y equals 2. Oh, well, that's got to be 0. All right, so there you go. That's a common point, 0, 0, 2. All right. So that's it. We're done. We have a common point and we have a direction vector. In fact, we have lots of direction vectors. Any scalar multiple of this will work. So we can now give our parametric equations for the line that's the intersection between those two planes. and have x equals, we'll take the x value of our point here. So that'll be what, yeah, that's just 0. So 0 plus, then we'll take the first component of our direction vector. So you can use any scalar multiple of this. So if you want to use 1, 2, 0, that's fine. But I'll go ahead and use that one that I had there. Y equals to, well, again, y is equal to, the initial value for y is equal to 0 there, plus 10t. And then z is equal to, well, that's 2, plus, and then that's 0t. Like this. Note, since one of your components is equal, since one of the components of your direction vector is equal to 0, you would not be able to write the symmetric equations to this because the denominator would be 0. So here we have to use the parametric equations. Here you would probably just write these as x is equal to 5t, y is equal to 10t, and z is equal to a constant 2. And there we go. That is the equation of the line that serves as the intersection between our two planes, that line there. And that makes us happy. All right. So now the next thing we want to look at, we wanted to find some distance in space. We have a few objects that we're talking about. We're talking about points, we're talking about lines, and we're talking about planes. Well, if we're going to be talking about these objects situated with respect to each other in space, we probably want to talk about how far apart they are. We want to be able to measure a concept of distance between them all. So the next two theorems involve distances between several of our objects. The first one, theorem, the first one is almost self-evident. Not quite, but the proof can simply be stated as well, really an illustration. The second one is a bit more involved. Theorem. We're going to start off with a plane we're going to call P. So let P be a plane and Q be a point not on P. Okay? So for illustration purposes, you have a plane and you have some point that's up here. It's not on the plane. It's up above or below or somewhere. It's floating somewhere not on this flat surface. Okay? Now, let's say we want to talk about the distance between Q and P. Okay? The distance from Q to the plane P is given by what? Well, let's see. How do you want to define distance? Well, obviously by the shortest distance, right? How far is my finger from this pencil? Oh, hundreds of millions of miles. If I go that way and circle around the solar system and come back around this way, right? Yeah, but that's not what we mean by distance. When we say distance, we mean the closest distance, right? The nearest between these 2 points. Same thing with this right here. I can define the distance to be from here to over there, or from here to over there, or from here to over there. This plane goes on forever, doesn't it? But I want the distance to be the closest distance. Okay, so how would I get to this plane the shortest way possible? Well, I drop straight down. Okay, so that's simply going to be the distance from Q to P along this path. Okay, well, what's that path? Well, it looks like it's sticking straight out of the plane. Oh, well, we know something that sticks straight out of the plane. That's called the normal vector. So that means we want something that is, we want something that's parallel to the normal vector. Okay, so, but maybe the normal vector that we found isn't over here. Remember, there's lots of vectors that are equivalent to each other. right? There's lots of vectors equivalent to each other. They just have to be traveling in the same direction. Let's say I computed the normal vector and it wasn't right there. Let's say it was, say, over here. Well, whatever, that's fine. It's all the same vector. So let's say I have a point P on my plane. And let's say that's where I computed the normal vector. Okay, so what? Well, connect P to Q. We can do that. That's easy. Just subtract Q from P. That creates a vector. So now what I want to do is I want to find out this component of the vector. I want to find out the component that's going in this direction. Well, this direction is parallel to this direction. Okay, so I want to figure out how much of this vector is going in that direction. It's called a projection. We've seen that before. So what we want is we want the projection of the vector PQ onto the normal vector. That'll tell you how much of this vector is going straight up away from the plane, or in other words, it tells you the distance from this plane straight up to Q. So that's what it's given as. The distance is given by the projection of is given by the projection of the vector PQ onto the normal vector. How much of this is onto this vector? Now remember, this projection would actually be a vector on its own, and we just want a distance. Distance should be a number, not a vector. Okay, so we'll take the magnitude of that. And then keep in mind how you compute the projection. When you take the magnitude of the projection, you take off the vector that's being multiplied by the scalar, and you simply keep the scaling factor. So that would be PQ dot N over the magnitude of N. That's just the projection formula. If you strip away that extra vector here, remember there's a scalar times the vector. If you take that unit vector, strip it off, leaving you just the scalar, that gives you the magnitude of the projection. So that's not a new formula, that's just the magnitude of a projection. Right? And here I realize this is, I left off what P is. Let P be a plane and Q be a point not on P. So right here, I guess I should say, let P be a plane, P, not the stylized curly one, but just like a regular letter P, be a point on the plane. And Q be a point not on the plane, not on P. Then the distance from Q to the plane is given by the projection of P to Q onto N, and you take the magnitude. So here the proof is, we could go into a little bit more detail, but you're not going to get much more than you get from this kind of illustration here. Unless we're in a formal analysis class, this is about as much as we need as a motivation for this. So instead, let's take a look at an example. Let's go and find the distance and again, but when we say distance, we mean the shortest possible distance. Find the distance between the point Q, which is given by 1, 3, minus 1, and the plane curly, fancy, stylized P, which is 3x minus 4y plus 5z equals to 6. You can tell we worked very hard to come up with examples, right? 3, 4, 5, 6. All right. You're going to need a projection of PQ. Okay, well, I have Q. I don't know what the point P is. Sure you do. It's any solution to this equation. Any one. So set x and y equal to 0, solve for z. Or set y and z equal to 0, solve for x. Or if you want to get fancy, set x equal to 1, y equal to 2, and solve for z. Or whatever. You need any solution to the equation of the plane. Because remember, P is just a point on the plane. It doesn't matter which one. So find any solution to this. That'll give you P. Okay, and then you can find the vector from P to Q. And then find the projection of that onto N. You say, well, what's N? You didn't give me N. Sure I did. Remember, N, the direction vector of the normal vector to the plane, which gives you the direction, is simply given by the coefficients of the variables. So here the normal vector would be 3, negative 4, 5. Right? So go ahead and give that a try. Pause the video, go through this, and find the distance between the point Q and the plane P. Once you're done, go ahead and unpause and we'll go through it together. All right, so here we go. Let's see, the point P. I'm going to go ahead and set y and z equal to 0. Why? Because 0 is a nice easy number. And also, x would be a whole number here. I wouldn't have to deal with fractions. This would lead to 3x plus 0 is equal to 6. Or in other words, that would lead to x equals to 2. So that means P is equal to the point 2, 0, 0. Then that means that PQ would equal to, we know Q already, let's subtract away P, 1 minus 2, 3 minus 0, negative 1 minus 0, which gives us the vector negative 1, 3, negative 1. We need the vector n, but that's found through observation. We can observe the vector n from the coefficients of the equation that gives us the plane. So here vector n would simply be 3, negative 4, 5. Okay. Now we want to find the projection of the magnitude of the projection of PQ onto n. Now one thing you can do is you can find the projection first and then take the magnitude. And that's fine. That'll get you the answer. It is slightly shorter, however, if you do this, because that will prevent you from having to find the full projection. You only need to find the magnitude of the projection directly. That being said, in this section and in this chapter, there are a decent number of formulas, which means if you have a limited capacity to memorize stuff like I do, I don't try to memorize new formulas if an old one will work. So if you have a sort of a limited capacity in terms of memorizing formulas, then you might just take the projection and take the magnitude. It'll take you an extra minute. Literally, it takes about an extra 1 minute to find the full projection and then take the magnitude. But if you are a little more capable of memorizing things than I ever was, then just go with this directly. So either way, we get a result. Here, if we take PQ dot n, let's see here, let's do it over here. PQ dot n, that's going to be, well, remember, multiply, and add them all up. That's going to be negative 1 times 3 plus 3 times negative 4 plus negative 1 times 5, which gives us negative 3 minus 12, which is negative 15, minus 5 to give us negative 20. Just like that. So the magnitude of n, let's find the magnitude of n. That's going to be, we're going to take, let me put it over here. The magnitude of n, we're going to go ahead and take the square root of the sum of the squares of each of those components. So 3 squared, negative 4 squared, and 5 squared. So 9 plus 16 is 25, plus another 25. Oh, that gives us a square root of 50. All right, so then that means that our distance is given by, here I'll say d for distance, is equal to, we want the absolute value of that dot product divided by that magnitude. Let's see here. We can simplify 50. Let's see. 50 is 2 times 25, and I can take the square root of 25. It's just the number 5. So it'll be 5 root 2. So that'll be positive 20 Take the absolute value, makes that positive. 20 over 5 root 2, which we can simplify. Right? That reduces down to 4 over root 2. Which we can even rationalize, right? I believe this textbook, if you look in the answers, it'll give everything to you in rationalized form. So here that would be what? 4 divided by 2. Well, that's just the number 2 times root 2. So that's our distance. And that makes us happy. Okay. So now, the other theorem that relates to distance, we talked about a point away from a plane. Let's talk about a point away from a line. So let L be a line in space. P be a point. You see, I'm actually learning from my mistakes. Be a point on L, and Q be a point not on L. I'm learning from my mistakes. Trust me, I'm going to make all new ones here. Let L be a line in space, P be a point on L, and Q be a point that's not on L. Here, we can draw these in space, but it's going to be simpler if we I'm going to draw these on a plane. Nothing from this theorem requires us to have a visual that's in a plane. For lack of a better thought is, hey, this can be in any direction we like. We can just take this and tilt our paper, tilt our head until this is perfectly flat. So since you can tilt things in any direction you want until it's pointed flat, I'll just go ahead and draw it flat to begin with. Whenever you have something like that where, yes, technically it can be in any direction, but since you can tilt it and you can move it until it looks exactly like what you want, flat, whenever you have something like that, the phrase is without loss of generality. That means, yes, I could draw it in a more general sense where it's oriented in some random direction, but by just tilting it and making it look nice, it'll be easier for me to draw, it'll be easier for you to understand, but it still means exactly the same thing. So here, without loss of generality, it's, in other words, yeah, we could draw it more generally, but it doesn't really matter. Without loss of generality, let's draw this on the plane. After all, these are drawn in, this is in 3D, right? It's coming left and out and up. But so what? It's still on a plane. It's on a flat surface. So as long as you have just a single vector, then you can always consider that as being on a plane. Right? Or even two vectors. You can consider those as being on a plane. All right, so here we go. Let L be a line in space. So here's my line. I'm going to draw it flat. Here's my L. Okay. We want P to be a point on L. So there's my P. And we want Q to be some point off of L. It doesn't necessarily have to be right above it, just somewhere not on L. It could be down here or up here. And again, without loss of generality, I'll draw it up here. You say, well, what if it's down here? Well, then flip your paper upside down and now it's up here, right? That's what we mean by without loss of generality. Yeah, it could be down here, but it would make a difference. Okay, so now what we want to do is we want to find the distance from Q down to the line L. So let L be a line in space, let P be a point on L, and let Q be a point that's not on L, somewhere floating up in space. Finally, for conditions, anytime you have a line, you can define a direction vector. Here we'll call the direction vector U. Is that what we called it before? Oh, actually, over here we called it V, didn't we? V was the A, the B, and the C. Whatever. That U is fine. We can go ahead and call U. So you see, I made another mistake, and I shouldn't have put the word "and" here because I wasn't done. You see, I learned from my mistakes, and I made an all new one. Q be a point not on L, and let U be the direction vector of the line L. Then the distance, and again, as always, we mean the shortest distance. The distance from Q to L is given by, here we'll say D for distance, is equal to the magnitude of the cross product of the vector PQ with U divided by the magnitude of the vector U. This one is a little less obvious than this one above. Thankfully, the heavy lifting's already done for us. This depends very much on a previous theorem that we had, an alternate definition of the cross product. So over here, I'm going to go ahead and say recall. Just let's remember something. From a previous theorem that we had in a previous section, recall that an alternate definition for the cross product, for the magnitude of the cross product, is if you take the magnitude of the cross product of two vectors u and v, that's equal to the magnitude of u times the magnitude of v, since those are both scalars. It's not a cross product or a dot product. It's just multiplying two scalars, two numbers, times the sine of the angle theta, where theta is the angle between the vectors u and v. Okay, so remember that one. That one's what we're about to use here. All right, so here you have the vector u, which is the direction vector along L. Here we could also define a vector from P to Q, because why not? Okay. Well, since we have two vectors, we can define the angle between them. We'll call that the angle theta. Okay. All right, so what? Well, you'll notice that this defines a right triangle with the distance that we want. Here's the distance that I want. I want to drop a line straight down from Q to P. All right, awesome. Okay, well, it's a little trigonometry. That should be a D for distance. Okay. The sine of the angle theta is opposite over hypotenuse. Okay, so I know that the sine of the angle theta is equal to the side opposite. Okay, well, that's my distance that I want, over my hypotenuse. Well, the hypotenuse is the vector P to Q. Oh yeah, but that should be a scalar. Okay, fine. The magnitude of the vector from P to Q. Oh, okay, so the distance I want, I can multiply this number over to the other side. So that's equal to the magnitude of PQ times the sine of the angle theta, where again, theta is the angle between those two vectors. Oh, I guess I should separate this stuff, right? That's the theorem up there, and down here we have the proof. All right, so that's the distance that I want. Okay, but notice that's really, really similar to what we have over here. Here, that's the magnitude of a vector times the sine of theta. Well, if I multiplied it times the magnitude of this vector u, right, then that would just be the cross product of that vector u with that vector pq. All right? So here we could say the magnitude of the vector u times the magnitude of the vector PQ times the sine of theta. Right? That vector magnitude times that vector's magnitude times the sine of theta is equal to the magnitude of the cross product of those vectors. So the cross product of u with PQ. Okay. Oh, but notice that that's just u, the magnitude of u times d. After all, that's your distance times this thing. Okay. Oh, but that d that I'm looking for, I can just take this and divide out on all sides. So here, if that means the magnitude of u times d is equal to the magnitude of u cross pq, I can divide both sides by this magnitude of u, and that's my result. The distance that I want is equal to the magnitude of, here the cross product is not symmetric. Here, this and this are different. But remember, the cross products are equal down to a sign. So if this is 12, this is minus 12. If this is 73, this is minus 73. But since the magnitude is positive anyway, it's kind of like the absolute value, then it won't matter which one's positive and which one's negative. So here I can just flip that around. So here that's the magnitude of PQ cross U. Without the magnitudes, I cannot flip those around. Right? These are not equal to each other, but their magnitudes are equal. And there's our result. The distance is equal to the cross product of PQ with U divided by the magnitude of U. My apologies, that one is a little disorganized here. So that's the end of our proof. All right, so let's take a look at an example of this one. Let's go and find the distance, and as always, we mean the shortest distance. Find the distance. From the point 1, 2, 1, negative 2, 4, and the line given by this set of parametric equations, x equals 2t, y equals t minus 3, and z equals 2t plus 2. All right, so given what we just saw, first of all, we're going to need to find a point P that's on our line. Well, that's simple. That's given to us by our parameterization. Remember, the symmetric equation is not symmetric. The parametric equations of a line are such that they look like x equals x naught plus a t, y equals y naught plus bt, and z equals z naught plus ct. So here, notice that you don't have any constant, so that x naught is equal to 0. Here your constant is a minus 3, so your y naught is equal to minus 3, and here your constant is equal to 2, so z naught is equal to 2. So that means that the point P on the line is 0, negative 3, and positive 2. Are there other points on that line? Of course, there's infinitely many points on that line, but that one works and it's fairly simple to come with. All right, so we find one point on our line. We can find the direction vector by looking at the a, the b, and the c, the coefficients on the linear parameter. In this case, 2t, 1t, 2t. Oh, that means that the direction vector u is given by 2, 1, 2. Just like that. All right, well, we have a point P. We also have a point Q, Q that is not on the line. We were given that, 1, negative 2, 4. Okay, so what do we want to do? We want to find PQ. We want to cross that with U and then divide by the magnitude of U. All right, so first of all, let's find PQ. The vector PQ is given by 1 minus 0, negative 2 minus a negative 3, and 4 minus 2. One, 1, 2. All right. Next, we want to take the cross product of PQ with U. Let's go and do that right here. I, J, K, I, J, K. Let's see, PQ is 1, 1, 2, 1, 1, 2. U is 2, 1, 2. And again, 2, 1, 2. And here we go. That is 2I. That is plus 4J. And that is plus 1K. Because apparently 1 times 1 is 2. That's what I thought. Just for a second, that's what I thought. 1 times 1 is 1K. Minus, and then we'll go back the other way. And that'll give us 2I. That'll give us 2J. And that'll give us 2K, it looks like. Just like that. So that's going to give us 2 minus 2, that's 0. So that's going to be 0I. 4 minus 2, that'll give us plus 2J. And then 1 minus 2, that gives us negative 1K. All right, so that gives us our PQ cross U. And I want to find the magnitude. Record that up here, 0, 2, minus 1. And I want to find the magnitude of that vector. So the magnitude of PQ cross U will simply be the square root of the sums of the squares of those components, namely 0, 2, and minus 1. So that's what, 4 plus 1, that's going to be the square root of 5. So now we have that magnitude, the magnitude of PQ cross U. Now we need to find the magnitude of U on its own and divide. All right, so we know the vector U that was found right here. The magnitude of the vector U is given by, again, the square root. We're going to take each of those components, square them, and add them together. So that's going to be 4, plus another 4 is 8, plus 1 more is 9. So the square root of 9 is just the number 3. And finally, we put that together. Our distance is the magnitude of the cross product of PQ with U, which we found to be the square root of 5, divided by the magnitude of the vector U, which we found to be the number 3. And so the distance between this point and this line, meaning the shortest distance between the point and the line, is given by root 5 over 3. And that makes us happy. For now, we're looking at these numerically. That serves the purpose of getting us used to using these things in a context, helping us see what they look like and what their results are. Oh, results are constants. In other cases, results are variables. In other cases, results are vectors. In other cases, results are lines or even planes. Right? So this is getting us used to using these equations and seeing what do they result in, what kind of answers do we get, and so forth. That being said, specific numerical values aren't necessarily important going forward. In later sections, we'll be using these formulas to compute distances in a more abstract fashion, meaning we're not going to care about a specific number. Rather, we're going to use the concept of a distance to expand some other ideas forward. All right? Same thing with distances between planes and lines. Same thing with equations of intersections or equations of lines or even equations of planes in their parametric form like we see over here. All right? So none of these things are necessarily important from a numerical standpoint, maybe sometimes, but often we'll be using the concepts without specific constants as a basis to further more advanced ideas. All right? Finally, the last thing for this section, There will be occasions where we're going to want to sketch things. Just like in any other class, a sketch is often not an end in its own. It's not for its own ends, rather. Instead, it's used as a way of gaining intuition. We want to see a visual to see if maybe it'll give us some kind of inspiration or some idea as to what we should do next. In the next chapter, we're going to be seeing a lot more of that. But for right now, we're going to give an example. There's no theorem or definition here, just an example of how we might sketch a plane. Planes are not terribly difficult to work with, which is why we start with them. And in later sections and later chapters, in fact, we'll see some much more complicated surfaces. Not only that, but we'll define surfaces a little more exactly. So here, we're going to say sketch the graph. In fact, let me just say sketch. Sketch, oh, let's see, what should we sketch? Let's try this here. We're going to go ahead and sketch 3x plus 6y plus 2z is equal to 6. Whenever you sketch something that's in 3 dimensions, unless it's something extremely simple that you've encountered before and you know how it works, chances are you're not going to graph everything at once. You're not going to sketch everything at once. You're going to use what are called traces. The way traces work is, okay, 3 variables, hard to work with. 2 variables, easy to work with. We've been doing that since grade school, especially with linear equations. We've been doing that forever. Okay, that would be easy to do. That would be easy to do. Okay, but I don't have this, or this. I have all of that. Okay. But let's pretend we have this. You say, you can't do that. You can't just throw something away. Well, I can, sort of. Because after all, these x, y, and z, they're solutions to this equation. And sometimes those solutions are going to have z equals to 0. So let's take for a moment what's called the xy trace. The xy trace is the solution or solutions, almost often multiple, where z is equal to 0. Okay. All right, well, let's see. What is that? Well, if z is equal to 0, you're just left with 3x plus 6y equals to 6. We can solve for y. Okay. That's going to give us, subtract this over, divide by 6. That'll give us y is equal to negative 1/2 x plus 1. Okay. Let's consider the xz trace. That's when y is equal to 0. Okay, well, if y is equal to 0, that's 3x plus 2y equals to 6. Oh, sorry, 3x plus 2z is equal to 6. Okay, there's no y to solve for. Okay, whenever it's just x and z, typically we solve for z. Why? No particular reason. It's just that's sort of a convention. It's used a lot. So here, if I solve for z, subtract your 3x over it this way, and that divide by 2. And so that'll give us z is equal to negative 3/2 x plus 3, like that. You could leave it that way as well, but this is easier for most people to graph, I think. Of course, if you disagree, you don't have to use the slope-intercept form. You're welcome to use the standard form. And finally, xy trace, yz trace. It takes no imagination to see which one's next. We're going to take the yz trace. And again, it takes no imagination to know how you find the yz trace. You set x equal to 0. All right, so it's going to be 6y plus 2z equals 6. Okay. Here I can solve for y. Subtract that over, divide by 6. So that'll give me what? Y equals negative 1/3 z plus 1. Like that. And again, if you prefer this, you're welcome to use this instead of the linear equation, instead of the slope-intercept equations. All right, so now how do those help? Well, these give us individual parts of our graph. Just like when you graph things in grade school, you plot individual points and then connect them to form a line. Here we're going to take that to the next level. We're going to start graphing lines and connect them to form planes. Or we're going to graph lines and connect them to form spheres or cylinders or other surfaces. But for now, we're sticking to planes. So let's go and see how to do that. Again, we're going to use a right-handed coordinate system. So here's our x, our y, and our z. And we should put some marks on here. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, like that. Okay. So now we're going to go ahead and trace these onto each respective plane. You say, well, what do you mean plane? You mean space, right? Well, whenever you have the xy plane, what happens when you set x equal to 0? Well, then you get the y-intercept. Okay, so even though I have a line that's on a plane, really, whenever I set x equal to 0, I don't look at the whole plane. I just look at that line. And when I set y equal to 0, I don't look at the whole plane. I just look at that line. And it gives me the x-intercept and the y-intercept. All right, cool. Same idea here. If I set one of these equal to 0, I'm not looking at the whole space. I'm just looking at this plane. If z is equal to 0, I'm not above up here, nor am I below down here. I'm right here on the xy plane. The xy trace is a line on the xy plane. The xz trace, since y is equal to 0, I haven't moved to the right or to the left. I'm right here, somewhere on the xz plane. And the yz trace, since x is equal to 0, I haven't come out of the paper, nor have I gone into the paper. Rather, I am right here on the yz plane. So let's go ahead and graph things on the appropriate planes. Here, if you want to use this one, that's fine. If you want to use this one, that's fine as well. Right? Here, it's sometimes useful to graph these on individual planes and then transfer them onto here, especially when you have more complicated things than just straight lines. So here, I'm going to go ahead and consider this trace. This is on the xy plane, hence the name, the xy trace. And whether I use this equation or this equation, it's going to have a y-intercept of 1. It's going to have a slope of negative 1/2. So down 1, right 2. So let me transfer that over here. On the y-axis, I've gone one step in the positive direction, so right there. And in the z direction, I've gone 2 steps in the z direction, so right there. Okay, that line becomes this line. You don't have to draw it twice. If you want to draw it just once, that's okay. But if you have a hard time visualizing that all at the same time, you may want to just draw it on a plane and then see, okay, where does it go here? On the y-axis at 1. Okay, y-axis at 1. On the z-axis at 2. On the z-axis at, on the x-axis at 2. Okay, on the x-axis at 2. Then connect that dot line. Those dots is the same as connecting those dots. Same thing over here. If I draw this just on its own separate little plane, notice that is not the xy plane anymore. That's now the xz plane. Okay, but still, that's going to be when x is equal to 0, z is equal to 3. So 1, 2, 3. And then when z is equal to 0, it looks like x is equal to 2. All right, because I'm going to go down 3 right by 2. So what does that line look like in space? Well, let's see, that's going to be along the z-axis, 3 steps up, 1, 2, 3. And along the x-axis, 2 steps out. Hey, look, that's the same one as it was right here. Okay, so looks like that. And then this third one, the YZ trace, is a line that exists on the YZ plane. X is equal to 0, so we don't worry about that one. Just the YZ plane. Okay. All right, well then here, when Z is equal to 0, Y is equal to 1. and that's got a slope of negative 1/3. So when it goes down 1, it goes right by 3. So, that actually does look a little strange because usually when we say y equals to, like right here, this variable is the independent variable. That's usually on the horizontal axis. And this one is usually on the vertical axis. It doesn't really make a difference, but since we're kind of used to doing something a certain way since what? The 8th grade? Is that when you first learned how to graph things? This variable is on this axis and this variable is on this axis. Let's not try to fight against years of habit. Let's do it this way. So here, when z is equal to 0, y is equal to 1. So that would be one step up right here. And then here, the slope of negative 1/3, down 1, right by 3. Once again, when z is equal to 0, y is equal to 1. And then my slope, down 1, right by 3. Okay, so it looks like my y-axis, I'm one step in the y direction. Oh, that was this point right here. Okay. And then over here, I'm 3 steps in the z direction. Oh, that was this point right here. Oh, okay. Well, of course it was, right? They're all on the same plane. So there we go. This is a visual of your plane. Your plane doesn't stop right here. It's not this triangle. It goes on forever, but it does contain this triangle. The idea being that if that's the origin, there's this plane between where we're currently sitting as the audience, as the viewers, and the origin. And this plane goes on forever in all directions, but the places where it intersects the xy plane, the xz plane, and the yz plane are given by this apparent triangle. However, the plane does go on forever in all directions, as planes always do. So this is a sketch of a plane. It's a quick visual representation. It looks like, oh yeah, it's touching the angle. It's touching the planes at these locations. But more importantly, it gives us a concept of the traces, which is something that we'll expand upon and use to far greater detail in later sections when we're looking at things that are a bit more complicated than just flat surfaces. But for now, that is it for the section. If anybody has any questions, comments, or problems on this, please make a note of those, reach out, and I hope everyone has a nice day.